Welcome to this explainer. Look, if you're just stepping out of middle school science and staring up at the giant mountain that is advanced chemistry, you might be feeling, well, a little overwhelmed. But don't sweat it. Today we're going to build your ultimate survival map. We're unpacking some basic concepts of chemistry, which is literally the bridge you need to cross into the really advanced material. We've taken all the noise, stripped it away, and distilled it down to exactly what you need to know. To get you completely prepped for your exams, we've organized this entire transition phase into 3 indispensable pillars: the laws of chemical combination, the mole concept, and reactions and solutions. Let's get into it.
Pillar number 1 is the laws of chemical combination, or as I like to call them, the fundamental rules of the game.
Now, your exams are absolutely going to ask you to identify these rules or use them in quick numerical problems. And there are 2 rules that are incredibly easy to confuse. First up, we have the law of definite proportions. Think of this as the rule of ultimate consistency. No matter where you get water from, whether you scoop it from a puddle, catch it in a rainstorm, or synthesize it in some high-tech lab, the ratio of the mass of hydrogen to oxygen is always, perfectly, 1:8. It's totally fixed. But then we have the classic trip-up trap, the law of multiple proportions. What happens when those exact same 2 elements combine to form completely different things? Think about carbon and oxygen. They can form carbon monoxide or carbon dioxide. If you fix the mass of carbon at 12 grams in both of those scenarios, the mass of the oxygen reacting will be 16 grams in the first compound and 32 grams in the second. That creates a beautiful simple ratio of 16 to 32, which simplifies right down to a clean 1:2. All right, moving right along to our second pillar, the mole concept. This is the core math you'll need from here on out. I know. The word mole practically strikes fear into the hearts of chemistry students everywhere. But listen, we're taking the fear completely out of it today. The mole is simply a standard counting unit. That is it. It's literally the exact same concept as using the word dozen. If I tell you to go to the store and buy a dozen donuts, you don't panic about the math, right? You just know dozen is a word for 12. In chemistry, mole is just a word for a specific number of things. But instead of 12, we use this epic, massive number, Avogadro's number, 6.022 times 10 to the 23rd power. Why so huge? Well, because atoms and molecules are impossibly tiny. We literally have to use a massive counting unit just to talk about them in practical, everyday amounts without losing our minds writing out endless zeros. So how do we actually calculate this stuff without overcomplicating it? You really just need this ultimate cheat sheet right here. 3 golden formulas to find the number of moles, which, by the way, we usually represent with a lowercase n. If a problem gives you the mass, simply divide that given mass by the molar mass. If it gives you a raw count of individual particles, divide that by our magic Avogadro's number. And if the problem gives you a gas volume at standard temperature and pressure, just divide that given volume in liters by 22.7 liters. If you master these 3 formulas, you can confidently crush almost any numerical problem they throw your way. Okay, pause for a second, because speaking of that last formula, I need you to burn this specific number into your memory: 22.7 liters. Here is a massive insider exam tip that catches so many students off guard. A lot of older textbooks, or maybe some older notes you found online, will tell you the standard volume is 22.4 liters. Do not fall for it. Standard IUPAC conditions now strictly use 22.7 liters for gas volume. Always use 22.7 unless your specific test instructions explicitly tell you otherwise. Bringing it all home with our third and final pillar, reactions and solutions. This is where we get into real-world stoichiometry. We've covered the laws, we've conquered the math, now it's actually mix some chemicals. When you do this in the real world, the chemicals almost never run out at the exact same time. One of them is going to dictate when the entire reaction stops. It's like hosting a barbecue. Let's say you have 5 juicy burger patties, but you only have 4 burger buns. How many complete burgers are you making? Only 4, right? That 5th patty just sits there. In this scenario, your buns ran out first, meaning the buns are your limiting reagent. It's the exact same thing in chemistry. The chemical that runs out completely is your limiting reagent, and it dictates exactly how much final product you can possibly make. Now, what happens when we start dissolving things into liquids? Well, you have to be able to measure exactly how strong your mixture is. You absolutely gotta memorize these 4 core concentration terms. First up is mass percent. That's simply the mass of your solute divided by the total mass of the solution times 100. Then we have mole fraction, usually represented by a big X, which is just the moles of one single component divided by the total moles in the whole mixture. And finally, the heavy hitters, molarity with a capital M, which is moles of solute per 1
liter of solution, and molality with a lowercase m, which is moles of solute per 1 kilogram of solvent. Now, you're probably wondering why we have two terms that sound almost exactly identical: molarity versus molality. Pay close attention to the showdown because examiners absolutely love to test this. The crucial difference is how they react to the environment. Molarity uses liters of solution, right? That's a volume. And because liquids naturally expand when they get hot and contract when they get cold, molarity is actually physically temperature dependent. The concentration literally changes if the room gets hot. But on the flip side, molality relies on kilograms of solvent. That's mass, and mass never changes with heat. 1 kilogram is 1 kilogram whether you're in a freezer or an oven. So molality is wonderfully temperature independent and perfectly stable.
Wow, okay, we have covered a tremendous amount of ground in this explainer today, from the fixed ratios of chemical combinations to making the mole concept as easy as ordering a dozen donuts, right down to the temperature dependencies of real-world solutions. As you take this big step, crossing the bridge into advanced chemistry, I really want to leave you with this one thought. If your study time is your limiting reagent, and let's be real, for all of us it definitely is, are you focusing your moles on the right formulas? Maximize your output by mastering these 3 core pillars first. Keep this explainer handy, review these concepts before your next big test, and you are going to absolutely crush it. Thanks for learning with us today and keep asking the right questions.